Okay, so today we're going to be doing 7.1, which is going to be graphing exponential functions. So key concepts and main ideas. An exponential function is in the form y equals b to the x, where b is greater than 0 and b is not equal to 1. It has a constant base b and a variable exponent x. So like every other function that we work with in this class, we have a, h, and k. We know that a controls stretch or compression and then possibly a reflection. And the reflection will always be over the line y equals k. Okay, it's always over the asymptote, which we'll talk about. And then, of course, you have horizontal shift and vertical shift. H is always horizontal. K is always vertical. And remember, horizontal shifts are always backwards. So if it's plus, it's actually to the left. And if it's minus, it's actually to the right. And that's due to the nature of the fact that the equation itself has a negative sign in it. And then the k is a vertical shift up or down. And if you don't have a k, your k is an implied 0. Okay, because obviously if you don't have one shifted up or down, it's just k of 0. And then we'll talk about what an asymptote is. An asymptote is an imaginary line that the graph approaches. Asymptotes of exponential functions correspond with the line y equals k. So let's go ahead and look at exponential growth. So I'll zoom in here while we do that. So if you're wondering what equation is graphed here, I'll just tell you. It's just a standard exponential growth function, y equals 2 to the x. Okay, so that's the equation that's been graphed here, if you're wondering. So the domain for all exponential functions is negative infinity to positive infinity. Now, before I do range, I'm actually going to move on to my asymptote. So asymptote is actually whatever y equals k is. And in this case, in this equation, what is the k value here? We don't have one. Yeah, it'd be like a plus 0. So that means your asymptote is y equals 0. Now, asymptotes with these particular types of functions are always horizontal lines. So it's going to be this horizontal line right here that covers up the x-axis. Okay, y equals 0. And your range is always going to be based on your asymptote. So is my function above the asymptote or below it? Above. Good. So that means my range is from 0 to positive infinity. So that means my graph starts down here and picks up here. Now, the reason I use a curved bracket instead of a square bracket for the end of my range is because 0 is not included, because you don't actually touch the asymptote. You can't actually plug 0 in, obtain 0 when you plug anything in. You can get close to 0, but you can't actually obtain it. And that's because there is no exponent. There's no number you can plug in for x that's going to make the answer become 0. Okay? What is my y-intercept here?
1.
Good. And end behavior. So I'll be talking about the end behavior on the left and the end behavior on the right. As you can see, the x portion is already filled in. Now over here on the orange, your graph can either approach, it's approaching what number here? As it gets smaller and smaller, it's getting closer and closer to what?
-3.
No, it's asymptote, which is 0. Remember, we're looking at f of x is y values, not x. And then over here, the graph is going up to positive infinity.
I have a question.
Yeah.
So when you're doing this, does it not go past 0?
Correct. It won't ever go past it.
Okay.
So that's why that one of your end behavior will always be correspondent of your asymptote. So whether it be this one or this one of them will always be the asymptote.
Okay, got it.
You're going to notice the asymptote come up a lot. It's going to come up in your range, of course the asymptote itself, and it's going to come up in one of the end behaviors. That's how you know you're doing it right. All right. Now we're going to talk about exponential decay. So domain is still the same, all real numbers. That's because the graph goes to the left and the right forever. Asymptote here is y equals 0. And if you're wondering what the original equation is, it's y equals 1/2 to the x power. Okay. So the asymptote is still right here. What's the y-intercept here? 1. Range? 0 to positive infinity. The range hasn't changed. And then end behavior. On this side, my graph's going up to positive infinity. And over here, it's going down close to 0. It doesn't approach negative infinity because it never goes past that line. So does everybody see why it doesn't approach negative infinity? Okay.
Wait, how do you get the range again?
Range is where the graph's going. So like, what's the lowest y value it takes to the highest? So it never actually touches 0, which is why we don't use the square bracket. We use a curved bracket. So a few other things to mention. I just want to point this out to everybody, a little tip. How do I word this? I worded it on here, so let me look at how I worded it. Okay. Exponential growth moves away from the asymptote as it gets bigger, as it goes to the right. And exponential decay, what do you think it does instead? Moves, yeah, closer or towards as the graph progresses. So you can see as this graph progresses, it moves away from the asymptote. As this graph progresses, it moves closer and closer to the asymptote. And that's the way you can differentiate between exponential growth and exponential decay. Make sense? All right. So we're going to try one of these on our own. How you identify the parent function, it's always y equals whatever your b is, so whatever to the power of x is, so 2 to the power of x. So whatever that number is already to the power, just to the power of plain x. Okay? Now in this case, we only have one transformation, and that's indicated by, is this an a, an h, or a k?
K.
Good, so it's shifted up 1 unit. So k is up and down. That also means my asymptote is y equals what? K, which is?
1.
1. So everybody see why your asymptote is y equals 1 there?
No.
It's always whatever your k is.
Okay.
So now what you're going to do is you're going to plug these values in for x into your function. So you see how I just take my function and I'm replacing the x with the x that was given to me. So if you do this in the calculator or mentally, 2 to the negative 2 power is 1/4, or 0.25. 0.25 plus 1 is 1.25. Because remember, a negative exponent brings it down to the denominator. So 2 to the negative 1 power is 1/2, or 0.5. 0.5 plus 1 is 1.5. Anything to the 0 power is, don't say 0. 1. What's 1 plus 1?
2.
Good. What's 2 to the first power? 2. 2 plus 1 is 3. And 2 to the second power?
4. 5.
So the answer is 5. Good. Alright, so now we're going to plot these points. We have negative 2, 1.25. That's like right about here. We have 1, 1.5. And then we have 0, 2. And then we have 1, 3. And then 2, 5. Before we connect these, we also want to graph our asymptote first, okay? Why would we want to graph our asymptote before connecting the graph?
So we don't go farther than the asymptote?
Good, so we don't go further then. And of course, it gets really, really, really close, like incrementally close to the asymptote. So if you go touch it, actually like physically touch it with your graph, it's okay. Just know that it doesn't in reality actually touch. Does that make sense? Okay. So domain for any of these is always all real numbers. What's my y-intercept here?
2.
Good. The range is going to be whatever your asymptote is to positive infinity if it's above the asymptote. If it's below the asymptote, it's going to be negative infinity to whatever that value is. Okay?
It'd be 1 to positive infinity, but the 1's not included.
Exactly. And then in behavior, over here, my graph is approaching the asymptote at 1. And over here, my graph is approaching positive infinity. Now the last thing we have to identify, exponential growth or decay, as it is growth. You can see that it's going away from the asymptote as we go to the right, but the other way to tell is the base bigger than 1? And it is. It's 2. Okay. So now, next one. As you can see, the parent function hasn't changed. It's just your base to the power of x, and our base happens to be 2. This is still exponential growth because 2 is bigger than 1. There's only one transformation on this graph, and it is A, H, or K?
H.
H, which means that we go 1 unit left. Good. Left 1 unit. Remember, H is always backwards from when it appears. That one is easy to forget. So, what is the K if we don't have one? 0. So now we're going to plug that in. Now remember, order of operations, you have to do the exponent addition first and then put it to the power. So that's why it's important that you put parentheses there. Okay.
Why are you adding 1?
Because it says to add 1. You don't flip all the operations. It just tells you which way it goes. You still apply it the same way.
Okay.
Yeah, don't overthink it. It doesn't flip. I see what you're saying though. So -3 plus 1 is -2. 2 to the -2 is 1 over 4, which is 1.25. -2 plus 1 is -1. 2 to the -1 power is 1/2, which is 0.5. This is going to come out 2 to the 0 power, which is 1. 2 to the first power, which is 2. And 2 to the fourth power, or 2 to the second power, which is 4. Alright? We're going to graph these. Before I connect them, I draw my asymptote. Oops, I accidentally undid that point. So when your asymptote is y equals 0, it's going to be the same as the x-axis. And then I'm just going to connect it to the best of my ability on here. It's harder to do on here, so you can make yours nicer. What's my y-intercept?
2.
Domain?
-infinity constant.
Good. Range?
0 to constant infinity not included.
Good. Over here, my graph is going toward?
0.
And over here, my graph is going toward?
Constant infinity.
Positive.
Good. Starting to get the hang of it now. It's not so bad. Alright. Now we're going to look at one that has multiple transformations applied. This one has 3 different transformations. So the parent is always y equals your base, which is 1/4, to the power of x. So your base to the power of x. Base is the one that has the exponent on it, so don't be fooled by the 2 out front. The 2 out front, is that A, H, or K? A, good. So my A right here tells me that we have a vertical stretch of 2. Now how do you differentiate vertical stretch and vertical compression? Vertical stretch is if that number is bigger than 1. Vertical compression is if that number is less than 1. So like between 0 and 1, like a decimal or a fraction. Now if that number is negative, it would also be a reflection, but it's not, so we don't have a reflection here. Now we also have that +2, which means we're left 2 units. And then lastly, what's the last one we have here? The -3 is? down 3 units. If it were x minus 3, it would be right, but it's not. It's at the end, it's the k. All right, so here we're going to plug these in. 2 to the 1/4 negative 3 plus 2 minus 3. Now, I'm not going to write out all the work on this one. You get the idea. I'm just going to tell you the answers because I've already done them. But you would go ahead and actually put this in the calculator. Or mentally, however you want to do it. So this is going to be 5, negative 2, negative 2.5. This one actually comes out to be a wonky decimal, so we just round it to the hundredths place. So whenever your decimal comes out to be like a long decimal, you're just going to round to the hundredths place, okay? Is this one growth or decay? It's decay because the base is between 0 and 1 instead of greater than 1. What's the asymptote here? Negative 3. Okay, so now we're going to plot our points. Negative 3, 5. Negative 2, negative 1. Negative 1, 2.5. Negative 2.5. 0, 2 point something, whatever it is. 1, it gets really, really close to 3. Now I'm going to draw in my asymptote. Connect your graph. So do you see how the vertical stretch affected the graph compared to the last one? See how much more stretched out this graph is than the previous one? You can kind of start seeing how these things affect the graph. Now my y-intercept is what?
2.88.
Good, negative 2.88. Domain, all real numbers. What's the range here?
Negative 3 to positive infinity.
Good. Now on the left, my graph is going up toward. Good. And then the other way it's approaching.
Negative 3.
Negative 3. Good. So one side is always going to approach the asymptote. We just have to determine which one. Any questions on that? All right. We'll go through this one a little quicker. This, okay. It's okay. You got it? I didn't plug in all the values that many. Okay, so the parent function is 0.5 to the x, and now we're going to describe the transformation. So this being negative tells me we have a reflection, right, over the line y equals k, and my k is 4. This number right here tells me we have a vertical stretch. This number here tells me, I meant to do it in red, it like didn't click. We have a shift 1 unit to the left. And then lastly, we go up 4 units. So everyone understand the transformations. Now this is exponential decay because this is less than 1, the base, whatever the base is. Now, like I said, I'm not going to plug all of these in. I will just tell you the answer. You can practice that work on your own. And of course, you can always check your work using Desmos, right? You know how to do the table function. We practice that a lot in here. I'm going to plot these points. And then my asymptote is what? Good, positive 4. So I'm going to graph that before I connect my graph, because that's going to tell me where to leave off. So it looks like this. Something like that. Domain is all real numbers. Now the range is different here. Y-intercept, same idea. What's different about the range in this one?
It goes from 4 to negative infinity. Or
Yeah.
negative infinity to 4.
So negative infinity up to 4 this time. So your range is just flipped around. So if your whole graph is below the asymptote, it's going to be the opposite, negative infinity up to whatever that point is. But it still relies on the asymptote, like I said it would. Now here, this side right here is going down to, good, while this side approaches 4. Alright, what do you think? You getting the hang of it? Okay.
Very